We're going to talk about operations with vectors that are specifically in two space. So a lot of these are going to be very familiar to us because we've been working with XY axes for many years now. And what I'm going to do is I'm going to relate these back to some equations that you used in the past. So a new topic here is when we're talking about R2, they've talked about unit vectors, which we did talk about a little before, that we can represent any projected vector in a form or scale multiples of our unit vectors. So the I is a unit vector that goes along the x-axis, and our vector j is a unit vector that goes along the y-axis. Okay? Both are unit vectors on the y and x-axis. OP, our positional vector, and we've talked about how to draw it, is any combination of A and B, and it can be written using unit vectors. And using unit vectors, we would say some scalar multiple of vector I plus some scalar multiple of vector j. Okay? And then what they've given us here is the magnitude of OP. Well, the magnitude of OP is the root of a squared plus b squared. What is this very familiar to, this formula? Distance formula or Pythagoras Theorem, right? And the distance formula is just Pythagoras Theorem rewritten, okay? And we'll talk about it. And this is your distance formula right here. That's exactly what it is when we're talking about this. And the only reason this is any different is because this is a vector that's not at the origin, okay? Vector AB is somewhere on our graph. Okay, so I know this is very theoretical right now. And then this talks about how to find our vector that's not on the projected area. So let's talk about the two examples they've done, and we'll relate them to a graph here. Let's say we'll start with a positional vector. We'll say it's at -6 and -3. Okay, so a positional vector here at -6, -3. Well, we know we go on the x-axis first and then on the y-axis. These are our points, x and y. So we go -6, -3. Here's our point P. Okay, we know we're starting at the origin, so we're going to have this will be considered vector OP. Okay, and we go to draw our line here. Here is our vector. Okay. Now, if we were to represent this as component vectors, remember we talked about I. All right, I as a color of purple and J as blue. Okay, so we have vectors I and J. This is a combination of many unit vectors, and I'll show you what one of the unit vectors would actually look like. Our first unit vector being I, in purple, is just the value of 1 along the x-axis, and our J unit vector is just the value of 1 along the y-axis. So if we were to go to represent this in terms of unit vectors, we would give it the scalar multiple of -6 for our vector I, because that's our x. So it's -6 vector I. And then we give it the scalar multiple of -3 for vector j. So -6 vector I, subtract 3 vector j. And this is our OP, so the positional vector, written as unit vectors. Okay? It's relatively simple. All we're really doing is taking our coordinates and we're using them as the scalar multiples of those unit vectors. What we're saying is if we take this unit vector and move it back 6, and then we take this unit vector and move it down 3, we'll be at this position here with our positional vector. Okay? Simple enough. Okay. The other thing they're talking about, and that really encompasses all of, oh, not that one. These two here start. The next one they're talking about is a vector that's not a positional vector. Okay? And they're discussing how you can make it a positional vector. So let's say we have 2 points on a graph. So instead now we make 2 points on a graph. And that was this part here. Let's say we have 2 separate points on the graph. We'll call them A and B. So A will be at 2 and 7. And B will be at -4 and 1. So first thing we're going to do is plot our 2 points. Point A is at 2 and 7. So here's our A. And B is at -4 and 1. So here is our AB vector. Now this vector, we need to make it a positional vector. We need to move the tail of this vector. Oh, I drew it backwards. It's supposed to be AB. This part should be here. This part should be down here. Okay. Follow its directions, right? So this should be AB. This positional vector, if we were to duplicate it, we'll get an idea what it's going to look like. If we were to put it at its origin, the tail, it would be something here. It could be a decimal, right? It looks like it's at -6 and -6, but we're not 100% sure. So what they're telling us to do here is they're telling us to figure out what that point would be. And in order to do that, they've given us a formula. This formula is written right... Oh, no, don't disappear. Too much, sorry. Formula is written right here, okay, of OA and OD. And the idea is that A plus C gives us our X values, and B and D gives us our Y values. What are they talking about when they do this? So we'll take our X2 and X1. We'll actually write the positions of each of these. So it's very similar to a slope formula we had before. To find our new position, we take X2 and subtract X1, and we take Y2 and subtract Y1. Okay? So we'll call this our first point and our second point, making this X1, Y1, X2, Y2. Okay? So we plug these values in. Our X2 being -4, subtract 2, which is our X1. Y2 being 1, subtract 7. And we end up at -6 and -6. So that's exactly what it looked like we were going to end up at, but we had to test it to make sure. We had to prove that this was correct. So our point P, if we were to make this a positional vector, which is exactly where we guessed it would be, right here at -6 and -6. Okay? So now the tail of this is at the origin, and our tip is at -6 and -6. And finally, there's one other thing they've given us a formula for. They want us to find the magnitude of this. Okay? So let's talk about the magnitude of vector AB. To find the magnitude of this vector, you would use your distance formula again, but an easy way to do that, if you've already put it into position, think of this again like a triangle. We can relate it to Pythagoras Theorem again. We know that I can make this a triangle by extending an arm here and an arm here, which means I have a right angle triangle. Okay? So instead of having to remember, if you already memorized the distance formula, that's great. But usually Pythagoras Theorem, everyone kind of remembers from when they're younger. Oh, that's not what I want to do. Oh, give me a sec. I gotta fix that. Okay, so like we said, we're going to turn this into a triangle. So instead of memorizing that distance formula, which they essentially had up there before, I know that this side of the triangle is 6 and this side of the triangle is 6. So according to Pythagoras Theorem, I would just take my 6 squared plus 6 squared is equal to the magnitude of AB squared, right? Or in other words, that this AB is known as our hypotenuse, our C in this case, right? C squared equals A squared plus B squared. So that's how we relate it. So now we're going to end up with vector AB. You bring that power of 2 to the other side, it becomes a root of 36 times 2 is 72. So root 72 is the distance, or the magnitude, sorry, not the distance, the magnitude of OP. And if you actually give me the root, anyone know it? 8.7? Great. Roughly, oh, 8 point something?
8.4.
8.4, okay. Oh, easy fix. Excellent. Okay. No, go away. Here we go. So that's everything we did with that page. That's everything they really want you to know in 2-space. So we can relate these to very simple ideas we learned long ago. Pythagoras Theorem, distance formula, finding points. That's all that we're really working with right now with operation.